Welcome to COMPOS' Year 10 Webinar 11. Today's topic is Newton's laws, which is probably one of my favorite topics, and certainly one of the topics that is really important to understand physics in general, and the approach that you take. It's easy to understand. They're quite easy to understand the laws, and there's a lot of maths involved. So that's why they're so popular, especially in entrance interviews, university interviews. So when you get to your university interview, you're very likely to be asked something on Newton's laws. They are quite simple, but they are tricky. They are tricky, I have to admit, Newton's laws. So let's start with Newton's first law. And Newton's first law basically says that motion is the natural state of things. So what do I mean by that? So Fed, forces, and motion. And if I open this and I just create a frictionless environment, that's important that it's frictionless, because frictionless means forceless. And I push a box. I push a box. So now the box is moving, and it's moving at 15.9 meters a second. And if I let it go, it will just keep moving. So Newton's first law says motion is the most natural state of an object. And so we're used to things being stationary, but that's because we have a lot of friction. If there was no friction, pretty much nothing would be stationary. Okay? So look at a gas. At gas laws, gas properties. Let's look at an environment with no friction. So, and a gas is a very good example, a very good approximation. So this is some gas molecules in a container, and you let them go, they just move. They just keep moving forever because there's no friction. They will bump into walls, they will bump into each other, but there will never be a situation where they stop. So like being stationary is unnatural in the universe. And if you think about it, well, it is. Like planets go around the sun moves around the center of the galaxy. The galaxies are moving apart from one another, and who knows what happens beyond the observable universe. Everything is constantly moving, and that's absolutely natural. And that's what Newton's first law says. It says that if there are no forces, an object will remain moving at constant speed in a straight line. If there are no forces, an object will keep moving forever at constant speed. And that speed could be zero, right? If you're stationary and there are no forces, you will remain stationary until something pushes you. Okay, so I hope that makes sense. Does it make sense to you? Type something in the chat if you fully understand what I'm saying. Do I need a Q&A? I'll switch on the Q&A. Oh, I need a list of participants as well, just in case. I see some thumbs up. Lovely. Newton's first law. Let's write it down. An object will remain will continue moving. Okay. Continue moving at constant velocity. In a straight line. Unless an unbalanced force acts. Now, this is the school. This is the school. This is the way you are taught Newton's first law in school. There's a little bit more to Newton's first law than what you're taught in school. And actually, what's the Newton first law is about saying that there are frames of reference in which this is true. Because when you say that you are stationary, what do you mean that you are stationary? I normally say, well, I'm stationary because I'm in the room and I'm not moving relative to my cupboard. I'm not moving relative um, um, to the door. But for all you know, I could be in a very fancy motorhome, and I could be driving down the motorway at 70 miles an hour. You wouldn't know the difference until you see the cupboard shaking on a pothole. Or if I was in a very fancy train that looks exactly like the inside of my house, you wouldn't know the difference. And uh, also, even if I am inside my house, which maybe I am, maybe I'm not, but my house is moving around with the planet at about 300 meters a second. It's moving around the axis of the planet. And the planet itself is moving at about 30 kilometers a second, roughly. I don't remember the exact number, but I'm moving. I'm stationary in the frame of reference of my room, but I am moving in the frame of reference of the center of the Earth. So when I say an object continues moving at constant velocity, I have to say, so Newton's first law, the full statement of Newton's, there exist inertial frames of reference in which an object continues moving at constant velocity in a straight line unless and but. And that's the full Newton's first law. Full statement. I modified it slightly, but that's the gist. What is an inertial frame of reference? You ask me. Probably you're interested. An inertial frame of reference is a frame of reference that is moving in a constant. So when you're saying, what is a frame of reference? Oh, my room is a frame of reference. I'm stationary with the respect to my room. So I'm measuring from my room. I'm measuring from the wall. Okay, if you want to say. There's a clock in my room, my watch. So a frame of reference is a set of rulers and clocks that I use to measure. And this could be attached to a room, could to a car, etc. Okay, so we say motion is relative. Yes, I'm stationary relative to my room, but I'm moving with respect to the center of the planet. Okay. Okay. Now, an inertial frame of reference. Examples in inertial frame of reference. A frame that is moving at constant velocity. Example: a train at constant speed. Or what else? A house. A house. A house has constant velocity. It's constant zero velocity. How do I unraise my hand? I'm not sure. Anyways, train at constant speed, a house, etc. A non-inertial frame of the reference, non-inertial frame is an accelerating frame. Accelerating frame. Example, train going around a bend. Train going around a bend. Or a a slowing down car. A car slowing down. So what do I mean by that? Look, important. Important. Newton's laws are only true in inertial frames of reference. Let me do a quick experiment. I put a marble. Oh, I put a golf ball. Much better than a marble. I put a golf ball in front of me, and I put a golf ball in front of me, and according to Newton's first law, it's not moving because there are no forces acting. And this is because I am in an inertial frame of reference. Okay, it's an easy thing to. Okay, of course, it's not moving. The ball is not moving. But now imagine that I put the same ball, I get into a train, and I place the ball on the table, and now the train leaves the station and it starts to accelerate. So if I'm facing forward, the ball will roll backwards. So suddenly, there are no forces acting on this ball, but somehow it started moving. Well, because to me, I am stationary. I don't care what's happening outside. I don't care what's happening outside. I'm inside the train. I put the ball on the table, and it starts to roll. And that tells me that Newton's first law is not true in this train. Because if there are no forces acting on the ball should not. Does that make sense to you? Do you understand what I'm trying to say? On a scale of 0 to 10, please, in the chat, vote. 10, I understand completely. So my room is inertial because if I put a ball on the table, it won't. A train is a non-inertial frame of reference because if I put the ball in a train that is accelerating, the ball will roll. And that tells me that inside an accelerating train, Newton's laws do not work. And that's important. So Newton's first law is probably the hardest Newton's law because it's very conceptual. You need to really, really understand what's an inertial frame, what's a non-inertial frame. Right. So we won't be making any measurements inside an accelerating train because it's a non-inertial frame, and therefore you cannot use those measurements to do any calculations with Newton's law. Only in non-inertial. Oh, sorry, inertial frames. Okay, so hopefully that makes sense. Newton's second law is more straightforward. It's very mathematical. It says mass is proportional to force is proportional to acceleration. Newton's second law says that the acceleration of an object is proportional to the resultant force acting on that object. And let's see if that makes sense. So if I take acceleration value, So I have a box, I don't need any friction. And if I push the box with 100 newtons, you can see that the acceleration is 2 meters per second squared. Now, if I push the box with 200 newtons, acceleration would be 4. And of course, if I push 300 newtons, acceleration would be 6. So that's what Newton's second law says. Acceleration is proportional to the force applied to the object. And mathematically, it can be written like this. The resultant force, the total force, is mass times the acceleration of the object. So in this case, we can calculate the mass. So because force is mass times acceleration, we can calculate the mass by dividing force by acceleration. So 200 divided by 4. So it's a 50 kilogram box. And let's check that this is the case. It is. It says that the mass of the box is 50 kilograms. Okay. So Newton's second law is quite easy to write down. Yes, in a train that is moving at constant speed, Newton's laws in general, not just the first one, all of them, will work in a train that is moving at constant speed, and all of them will not work in a train that is accelerating. Okay, so Newton's second law also doesn't work in an accelerating train. Or the third, or the conservation of energy for that matter. So pretty much all most laws of mechanics will not work in an accelerating frame of reference. Okay. Not in an accelerating train. Of course, Newton's laws work in an accelerating train. They don't work in an accelerating frame of reference, and that's a subtle difference. Um, okay. Um, okay. Right. So Newton's second law. Now, how do you apply Newton's second law? How to apply Newton's second law? R means resultant. Fr is the resultant force. That's the total force. And yeah, mass is mass. Yes. An accelerating train is an accelerating frame of reference. Okay, we're getting into nitty-gritty details. Okay, let me try to explain what I mean by that. Imagine you are inside a train and you drop a ball. And in the frame of reference, so the train is moving. How does the ball move? Well, in the frame of the train, the ball just falls down. The ball just goes bam in the frame of reference of the train. The ball just falls down. Ball falls vertically. But in the frame of the ground, with respect to the ground, sorry, I don't know what's going on. In the frame of the ground, the ball will fall like this. Ball. A parabola. Okay. Now, if you're taking measurements in the frame of reference of the train, or you could say the ball has moved 0 horizontally because it's not moving. It's with respect to the train, it just falls down. It doesn't move horizontally. But with respect to the ground, it does move because as the train travels, the ball travels with the train, and the ball travels a certain distance horizontally. Right. So if you are inside an accelerating train and you're taking measurements from the train, so you're taking measurements from the wall of the train, for example, if you're measuring the distance from the wall of the train, then Newton's laws will not work. But if you're in an accelerating train, but you're taking measurements from the ground, which is stationary, then Newton's laws will work. And that's the subtle difference. So you can be inside an accelerating train, but it depends on where you're taking the measurements from. You're taking measurements from what? Right? Because once again, motion is relative. If two cars are on a motorway and they're both traveling at 70 miles an hour, they are stationary relative to each other, but they're moving at 70 miles an hour relative to the ground. And they're moving with 140 miles an hour in the frame of reference of the car that is moving in the opposite direction. So when you say you're moving, you have to say relative to what? I am, if I'm saying my speed is this, relative to what? Speed is always relative. Acceleration is absolute, and that's another thing. And this is touching a little bit of Newton's law, sorry, Einstein's laws. We won't go there, but hopefully, um, yes. So speed is relative. There's no way, if you are in a train that is traveling at constant speed, and this train is very, very smooth, and the windows are closed, there's no way of telling if you're moving or not. There's no way of telling how fast you're moving. You could be moving faster than sound, you wouldn't know it. There's no experiment that you can perform inside a train that is moving at constant speed that will tell you that this train is moving. However, if the train is accelerating, you can easily tell that the train is accelerating because you just put a ball on the table and the ball starts moving randomly. Well, not randomly, it starts moving. And that tells you that the train is accelerating. And you feel that acceleration. Yes, if you sit in a chair in a train and the train starts to go fast, you feel that. Right? If you've ever took the train to the tunnel, through the tunnel to France, it's quite fast and accelerates. You could feel that sometimes. You could feel the acceleration. You can never feel speed, but you can feel acceleration. And that's how you see, that's the difference between accelerating and non-accelerating. Okay, I've spent half an hour. We haven't even touched the first problem, and there are 8 of them. So let me try to remedy that. The car burns fuel and loses mass. Well, acceleration would increase because if you see that if the mass if the mass decreases and force is constant, then acceleration would have to increase. Right. How to apply Newton's second law? First, you draw a free body diagram. A free body diagram. And this is a diagram that shows the forces acting on the body. Shows forces acting on the body. 2, split the forces into horizontal, into two directions, two different directions. Split forces into components if necessary. And 3, write down mass acceleration equals well, the sum of forces. And I'll show you how to do this. Newton's third law, I'll show you how to do this. So example. Imagine you have a box and it's being pushed by 3 forces. It's 3 forces, F1, F2, and F3. And the box has mass m. Now, you need to assume acceleration. Like if you know the direction of acceleration, you show that acceleration. If you don't know, just guess. So I'm assuming the box will move to the right and accelerate at acceleration a. So what I do is I write down mass times acceleration of the box is the total force acting on the box. So there are 2 forces helping us. There's 2 forces that are helping us move, and 1 force that is not helping us. It's pushing the other way. So what I naturally need to write down is F1 plus F2 minus F3. And that's how I write. This is Newton's third law. Newton's second law. Sorry. Second law. Hope that makes sense. Speed is not a force, no. That is a question. Speed is the magnitude of the velocity. Okay, Newton's third law. Newton's third law is just every action has an equal but opposite reaction. Every action has an equal but opposite reaction. So if object A exerts a force on object B exerts an equal but opposite force of the same type on object A, sorry. Okay, that's the way I would recommend you remembering Newton's third law, not just actions equal reaction, because action equal reaction is not good enough. What do you mean by action and reaction? So imagine you have a wall and you push on the wall. So you lean against the wall and you push. So this is me pushing the wall. Me pushing wall. So A pushing B. A is I am A and B is the wall. So that means that the wall is pushing me with, so wall pushing me. So B pushing A. So A pushes B, B pushes A. Basically, what Newton's third law says, forces always come in pairs. You cannot have one force and not have the counter force. So if the ball falls on my head causes the ball to stop. That means my head is pushing the ball, right? My head makes the ball stop. Whereas the ball pushes on my head, leaving a bruise or a crack or worse, right? If my phone is on my hand, my phone is pushing on my hand and I can feel that force. I can feel the force of the phone pushing my hand, but that also means that my hand is pushing on the phone, not letting it fall through. Because if I remove my hand, the phone falls down, of course. Okay. Hopefully that makes sense. So that's Newton's third law briefly. So let's look at some applications. A person stands on digital scales in a lift. During the journey, the scale reading are as follows. It reads 90 kilograms for 2 seconds. So I don't know if you've ever taken digital scales into a lift, but they change during your journey. They change readings. Then it's 70 kilograms for 4 seconds and 50 kilograms for 2 seconds. Determine whether the lift is traveling upwards or downwards. Okay. So there's a lot of stuff going on in this question. It's a really good question for understanding of Newton's laws. So this is a person, and they're standing in a lift, and the lift is connected by cables, and there's a cable connected to some kind of motor. We don't really care about any of that. When we draw a free body diagram, we draw only one object. Free body diagram. Only draw one object. In this case, this is the person. The person is the object. Okay? And what are the forces acting on the object? Well, there's a gravitational force. There's a weight of the person. So mg, mass times gravity. Mg is the weight. And in the feet of that person is the normal reaction force. So the normal reaction force, normal. So that's the force that's not letting you fall through the ground, a normal reaction. And okay. And it says that the reading on the scale. So what is the reading on the scale? Well, the reading of the scale is actually the normal reaction force. This is the value of the n, because the scales do not measure your mass. The scales measure how hard you press on the scales. And you can easily verify that. You can push them with your hand and they will show you the force of pushing, not your mass. But when you're standing still on the scales, they will show your mass because the mass is equal to the normal force, if that makes sense. So for the first section for this first section, you can see that, well, okay, it's a 70. This is Well, okay, we don't know. We don't know. Let's assume for the first that the acceleration is up. So first, second, third. First, assume lift accelerating up. Lift accelerating up. And we can say that, okay, well, if lift is accelerating up, we write Newton's second law. And Newton's second law is mass times acceleration equals the forces that help you accelerate. So normal force is helping you to accelerate, and minus the forces that are preventing you from accelerating, which is mg. So ma equals n minus mg. I hope that makes sense. So mass times acceleration is the resultant force, but the resultant force is n minus mg. So n is pushing you forwards, mg is pushing you backwards. And here, that means is 900 newtons. This is 700 newtons, and this is 500 newtons. So we know that n is 900 newtons. So mass times acceleration is 900 minus mg. And okay, for simplicity, I just have to say that mass of the person is 70 kilograms. It doesn't say that, but it is. It is. So 70 times A equals 900 minus 70 times 10. So acceleration is 200 divided by 70, which is approximately what? No, that doesn't make any sense. 200. Oh yeah, it does make sense. 200 divided by 17 is 2.86 meters per second squared. Okay. That's a very good question. Thank you for that question. Right. So in Newton's third law, normal reaction does not equal to mg. That is a very common mistake. Because when I say that normal reaction, action and a reaction, my feet are pushing the floor of the lift. And the floor of the lift is pushing my feet up. So this is a Newton's third law pair. Because it's the forces of the same type is a normal contact force. So my feet are pushing the lift and the lift is pushing me. Normal reaction and mg are not Newton's. It's not action and reaction. Mg is not action and n is not reaction. Because n is floor pushing person. Mg is the planet pulling person. It doesn't work. Do you understand why it doesn't work? Because floor is pushing person. The Newton's third law pair would be person pushing floor. But we don't draw that force because that force acts on the floor. So there's normal reaction. So N is the floor pushing the person, and the counterforce is the person pushing the floor. But we don't care about that force because we're only interested in the forces acting on the person. Does that answer your question? Um, okay, you can write in the chat. Chat is easier because, right. mg's, okay, so acceleration is 2.86 upwards. Upwards. Now, 2, in the second section of the path, so it's 70. So mass acceleration is equal to the normal force minus mg, but the normal force is 700, so mass acceleration is 700 minus 700, and that means it is 0. So acceleration is 0 meters per second squared. So constant velocity. And finally, 3. Now the lift is decelerating. Lift decelerating rating. So you have acceleration down. So you're moving up. The lift is going up, but the acceleration is down. And therefore, you can the normal force and mg. So mg would be greater than normal force. So mass times acceleration is mg minus n. It's the other way around. So mg is helping you decelerate, and n is kind of preventing you from decelerating. And so 70 times a equals 500 minus 700. So acceleration is minus 2.8586, 2.86 meters per second squared. And so what's happening? So first, it's trialing upwards and upwards. Upwards. First is upwards and accelerating, and then okay, upwards and accelerating, then constant speed, and then yes, the actual mass of the person is 20 kilograms. Find the magnitude of this acceleration. So that's plus 2.86 and minus 2.86 meters per second squared. Meters per second squared. Sketch the graphs of acceleration, velocity, and displacement. Okay, so this is my favorite part. So acceleration is easy. So for 2 seconds, and then for 4 seconds, and then for another 2. So we'll start with the acceleration time graph. This is 2, 6, 8. So for 2 seconds, the acceleration is positive. So it's plus 2.86. Plus 2.86. Then acceleration is 0. For 4 seconds, acceleration is 0. Good. And then acceleration is negative. Acceleration is negative 2.86. Velocity. So first, the lift is accelerating. The lift is accelerating. So for 2 seconds, it's accelerating. So 2.86 times 2. 2.86 times 2. So it reaches a maximum speed of 5.72. So it accelerates, reaches a maximum speed of 5.72 meters per second, because 2 seconds at 2.86, okay, right? Velocity is acceleration times time. Change in velocity is acceleration times time. And then for 4 seconds, the lift travels at constant speed. And then for 2 seconds, the lift decelerates and stops. Okay. And you can calculate the total, you can calculate the distance traveled in the first 2 seconds. So that's 5.72 divided by 2. Oh no, that's 5.72 meters. Then for 4 times 5.72. That's 22.88 meters and 5.72 meters. So this is the velocity time graph, and then the displacement time graph. You're always moving upwards. So for 2 seconds, you're accelerating. Then, so 2, 6, 8. And this is the displacement S. Displacement. So first you travel for 5.72 seconds and you're accelerating. So the graph goes like this, it's curved. Okay. Then it's a straight line. And then it curves up like this. So acceleration, constant speed, deceleration. Acceleration, constant speed, deceleration. And this is 5.72 meters. This is 5.72 plus 2.88, 28.6 meters, and finally plus 5.72, 34.32, 34.32, 32 meters. Webinars, there's a timetable of webinars. If you go to our website about COMPOS webinars, here's the timetable. Usually it's every 2 weeks. This week is an exception because I was away and I couldn't do a webinar, so that's why we have 2 weeks, 2 webinars in a row. Anyways, all right, hopefully that makes sense. Also this. For question B, wasn't the mass just an arbitrary value? How do we know that it is correct? It's not arbitrary, so I knew the answer. I just assume we knew it. Let's assume person mass. Just to save time, honestly. Right, so a balloon of mass m is descending vertically with constant downward acceleration. So we have a balloon that is descending. And it's accelerating downwards. A ballast of mass m. So when a balloon is falling rapidly, what you want to do is you want to throw something out. And balloons usually have special bags of sand that they can just throw out in case they're starting to fall. So they throw out the ballast and they start rising again. In this case, they don't start rising, they just continue moving. So they're accelerating and they are releasing some mass. So some of the mass is being released. And then mass m. And the balloon is mass m. That's the total mass with the ballast. Okay. So let's look at the forces before release. We have a balloon of mass m. So what forces are acting on the balloon? Well, there's the mass of the balloon, mg, mass times gravity. That's the gravitational force. That's the weight of the balloon pulling down. And then there's the upthrust force, u. And it says we can ignore resistance is negligible. So we can ignore air resistance. And the balloon is accelerating downwards. Right, so we can write Newton's second law. Newton's second law says mass times acceleration is is the force pulling you in the direction of the acceleration minus the forces pulling you against, minus u. Okay. After release. Now the balloon has a mass of m minus m small, so the mass has decreased. Now you still have the same upthrust force, but now your downwards force is m minus m times g. And the acceleration, well, the acceleration is 0 because you're not accelerating. It says a constant speed. Right. So these are the two free body diagrams for the balloon. And we can write Newton's second law. Mass minus mass, m minus m, times acceleration of the balloon, which is 0, is equal to m minus m times g minus upthrust. And that's 0. So in other words, 0 equals m minus m times g minus upthrust. And now we just use these are simultaneous equations. What are we looking for? We're looking for the free body diagram. Write Newton's second law of the motion before the ballast is dropped. Write down Newton's second law of motion after the ballast is dropped. Yes, and hence show that the acceleration. So we need the acceleration. Okay, cool. We can find u from the second equation. So u is equal to m minus m times g. And you can sub that into here. So mass times acceleration equals mass times g minus m minus m and g. So ma equals mg minus mg plus mg. Mg cancels out, and we have mass acceleration equals mg, and acceleration is equal to mg over m. That's the acceleration of the balloon before the mass has been released. Okay. Next one. So I'll speed up a bit because I want to go through the questions. They are very similar to the questions in the assignment, so I think they are valuable. They would be valuable. So a mass is suspended from the ceiling of an accelerating lift. Okay, so we have a lift, and we have a mass m1, and we have a mass m2, and electric mass hangs below it on a light string. The tension in the lowest string, is 19.6 newtons. Find the tension in the upper string. Okay, so starting with free body diagrams, we draw M1. We draw the first object, and there are three forces acting. First, there's the tension in the upper string. Let's call it T1. So the string is pulling the mass up. Now on the bottom, there's another string attached, and it's pulling it down, T0. And also we know that there's a gravitational force, which is M1G. And 19.6. Okay, that's a very good one because we don't know which way acceleration is. Acceleration, we don't know if it's accelerating up or down. So we're going to guess. I'm going to assume that the lift is accelerating up. That's a guess. Doesn't matter. It doesn't matter which way it accelerates, as you will see in a minute. Okay, so we write down Newton's second law. Newton's second law, as I said, mass times acceleration. Mass times acceleration is the sum of forces. Or in a different way, you can write it like this. Mass times acceleration is equal to the positive forces minus the negative forces. What do I mean by that? Positive forces help you move forwards. Negative forces prevent you from moving forward. Not forward, accelerate forwards. So m1, that's the mass of the block, times the acceleration, which is upwards, is equal to the forces that are helping you, which is T1, minus the forces that are not helping you. So minus T0 and minus M1G. I hope that makes sense. And I just draw a box around it because that's my first equation. The second equation, now I go to the second object, M2. And there are only two forces. There's M2G, so the gravitational force pulling down, and the rope T0. T0 is the bottom rope pulling it up. And we know that because if the first mass is moving up, then the second mass must be moving up. And the acceleration is the same. So A1 has to equal to A2 because they're connected by a string. All right, so mass acceleration equals the forces helping you go forwards minus the forces not helping you go forwards. So M2G is T0 minus M2G, and that's your second equation. Now, what do you don't know? Oh, sorry, acceleration. Acceleration. Ah, so you kind of can find the acceleration from here because M2 is 3 kilograms. 3 kilograms multiplied by A is equal to T0, which is 19.6, minus 3 multiplied by 9.8. Yeah, G is 9.8 in this particular case, meters per second squared. Okay, so we can straightforward find A. A is what? 9.8. 19.6 minus 3 times 9.8 divided by 3. It's negative 3.27 meters per second squared. Remember, I said we're going to guess the direction of the acceleration, and we got a negative result. That means acceleration is down, right? Lift is accelerating down, not up. Lift accelerating down, not up. But that doesn't matter because that doesn't change anything on the calculation side. So mass 1, which is what? 2 kilograms. 2 kilograms multiplied by minus 3.27 equals T1 minus 19.6 minus 2 times 9.8. So here we can find T1 is 19.6 plus 2 times 9.8, which is 19.6, minus 2 times 3.27. So T1, so that's the acceleration times 2 plus 19.6 plus 19.6, which is 32.7. 32.7 newtons. That's the tension in the upper string. Yeah, that's the answer. Okay. Next question, friction. So friction is very weird. If you look at friction, so let's go to this one. Values. All right. So if I push the box with 50 newtons, the friction is also 50 newtons. And that's why the box doesn't move. If I increase the force to 55, the friction increased to 55. If I increase the force to 60, friction becomes 60. So it looks like however hard I push, the friction will match the applied force. Right. Friction, always forces of friction is applied force. And if we draw the graph of the friction force versus the applied force, we will see that it is a straight line from the origin, like this, up to a certain point. Because if we keep increasing the force, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Here we go. All the way up to 123, it was the same, and then suddenly the box started to move, and the friction force dropped to a new value. So if we keep drawing the graph, so it reaches a critical value, then it drops to a new value. And what happens next? Let's see if we increase the force. We increase the applied force, but the friction force doesn't change. Right? And even if we decrease the applied force, the friction force stays the same. Friction force is just 92. It looks as if it's fixed. And it is. Once the box is moving, the friction force has a fixed value and it doesn't. So when the box is not moving, the applied force is equal to friction force. This is if box not moving. And force of friction has a fixed value if the box is moving. Right, that's how the graph looks like. And that fixed value is equal to the coefficient of friction times the normal reaction force. If box is not moving, and force of friction is equal to mu multiplied by n, where n is the normal reaction force, if box is moving. We call this static friction. And this we call dynamic friction. Right. Okay, hopefully that makes sense. That's how the force of friction behaves. It obviously depends on the force of contact between the two surfaces. Coefficient of friction is just how rough the surfaces are. The rougher the surface, the higher mu. So for example, mu for ice would probably be like 0.05. Mu for the carpet, depending on what you feet on carpet, like feet on carpet would probably be, I don't know, 0.8 or something like that. Tires on road are approximately 0.9, etc. So it depends on this surface. So wood on ice. On ice. Don't quote me on these numbers. These are just I took the numbers out of my head. They might be not true at all. But the coefficient of friction, it just tells you how much friction, how much there's a friction force depending on the normal reaction force when you're skidding, like you're sliding on a surface. Because if you're stationary on a surface, the friction force is just simply the applied force. So there's a critical value of the maximum value of static friction force. Okay, that's fine. Sorry. Whew. A bit overwhelmed. A crate of mass 25 kilograms rests on a horizontal floor. The coefficient of friction of the static friction, mu s, is 0.4, and the dynamic friction is 0.25. A horizontal force is applied to the crate. Find the friction force and the acceleration of the crate when the applied force is 40 newtons. Well, if the gravitational force is 250 newtons, that's the weight. So the normal reaction force, so mg, is 250 and is also 250 because the box is not moving up and down newtons. And that means that the maximum value of static friction is mu s multiplied by the normal force, which is 0.4 times 250, and that is 0.4 times 250 is 100 newtons. 100 newtons. So if the applied force is less than 100 newtons, the box would simply be stationary. So 40 newtons is less than the maximum value of the static friction. So that's less than 100 newtons. Therefore, crate is stationary. And therefore, the friction force is applied force is equal to 40 newtons. And the crate is just about to move. Just about to move, so it's not moving yet. Once again, and it's 100 newtons is not more than the, so that means friction is applied force, and that's 100 newtons. If the crate is already moving, then the friction force is mu dynamic times the normal reaction force, because it's a moving dynamic force, mu dynamic, and that's 0.25 times 250. That is 0.25 times 250. And that's 62.5 newtons. So yes, in this case, acceleration is 0. The first one, acceleration is 0 because the box is stationary. Now, for this one, the applied force is 100 newtons, but the friction force is 62.5 newtons. So mass, sorry, it's a bit of a mess. For question C, you have 100 newtons, and the friction force is 62.5 newtons, and the mass of the crate is 25 kilograms. So we write Newton's second law. Newton's second law, mass times acceleration equals 100 minus 62.5. So mass is 25. So 25A equals 100 minus 100 is 37 37.5 divided by 25. Acceleration is 1.5 meters per second squared. 1.5 meters per second squared. Acceleration is 1.5 meters per second squared. Finally, if it's 180, so 180 is definitely moving. So D, the box is moving, so it's 118 newtons. The friction force is still 62.5 because it's equal to mu times n, and it's 25. So mass acceleration is 180 minus 62.5. Acceleration is 180 minus 62.5 divided by 25. That's 4.7. 4.7 meters per second squared. Okay. So the friction force, so in this case, the friction force is 62.5 newtons, and acceleration is 4.7 meters per second squared. All right, so hopefully that makes sense. If you exceed, so there's a maximum value of static friction, but that's once you exceed it, your friction is just constant. Two blocks are stacked vertically. The bottom block has a mass m. It has a mass m. The top block has a mass m small. Coefficient of friction between the blocks is mu2. So mu2 is the friction between the two blocks, and the bottom block is mu1. A horizontal force applied to the bottom block, so F. Find the minimum force required for the top block to begin slipping. That's a good question. Why does a friction decreases at a certain point? If you ever try to move something heavy, like a bed, you push, 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 and then suddenly once the bed starts moving, the friction drops. There's many reasons for that. Well, basically the legs dig into the carpet, deep into the carpet. Generally speaking, when two surfaces are in contact, they get closer. After a while, they sort of stick together, right? And then you max friction. It's not max friction coefficient. We have static friction and we have max max static friction. Maximum max value of static friction, maximum value of static friction, and that's mu s times n. So static friction, static, is always less than or equal mu s times n, and dynamic is always equal to mu d n. Right. For simplicity, in most cases, we will just say that mu s is equal to mu d. For simplicity, mu s is equal to mu d is just mu, and then static is less than or equal mu n, and F dynamic is exactly equal to mu n. And that's a simpler model. Basically, that says that friction doesn't drop after once you start moving. But generally speaking, if you move something, if I were to move my cupboard, I would have to push harder to get it to move. And once it is moving, it's actually easier to okay, but I sort of have to rush. I have 15 minutes left. And I really want to go through well, hopefully most of the questions are okay. So we pull the bottom block out of the top block. So basically, it's like we pull a napkin. We put a glass on the table on a napkin, and we pull the napkin. It's the tablecloth trick, and we pull. So let's look at the forces acting on the top block. So top block. The top block, well, there's no one pulling it, but there's a frictional force. There's a friction between the bottom block and the top. And so there is the mg, the weight. There's the normal reaction force. Let's call it N1. And then there's the friction force. So if you're pulling the bottom block from underneath, friction will push the top block to the right. Right? So if this is the bottom block, and this is the top block. So if I pull this way, the friction will pull the top block in that direction. That's why it's moving, right? So if I pull that way, the top block moves with the bottom block because there's friction. If there was no friction or not enough friction, the top block would slide off. Once again, if I pull too hard, it just slides off. But if I pull it on gently, it will accelerate with the top blocks. And that's what we're trying to establish here. What's the maximum force that I can apply to the bottom in order for it, so what's the minimum force I apply to the bottom for it to start sliding? And that friction force is mu1 n1. Right, so for vertical forces, we can safely say, so vertical forces, mg must equal to n1. Horizontal, so it's accelerating to the right, a, mass 1 times acceleration is mu1 n1. It's the only force acting in that direction. And this is, oh, there's no m1, mu1. Okay. Bottom block. And then, so it has a mass m big. Now, what are the forces acting on that block? Well, there's gravitational force pulling down, so there's mg. There's the top block pushing us from the top. The top block is pushing N1. And then there's the ground pushing from below. That's N2. And there's a frictional force from the ground preventing you from accelerating, which is mu2 N2. And there's a frictional force from the top block, because if the bottom block, if there's friction between the bottom and the top block, so there's a friction force, another mu1 n1. So this is friction from the ground, and this is friction from the top block. And of course, we are pulling here. We're pulling with a force F. So these are all the forces acting on the bottom block. And we can write vertical forces. Vertical forces is that N2 must equal to N1 plus mg. Horizontal is that it's accelerating to the right. Accelerating. So mass m big times acceleration must equal the force of pulling minus mu1 n1 minus mu2 n2. So we've got 4 equations. Okay, so n1 is mg, so we can write ma equals mg, mu 1 mg. M cancels, and you have acceleration is mu 1g. Now for the vertical forces here, N2 is that, so we can sub that into here. Ma equals F minus mu 1 N1. N1 is just mg minus mu 2 multiplied by mg plus mg. Ma equals F minus mu1 mg minus mu2 mg minus mu2 mg. And here we know that acceleration is mu1g, so m mu1g equals F minus mu1mg minus mu2mg minus mu2mg. So F finally is this mg plus mu1 mg plus mu1 mg plus mu2 mg plus mu2 mg. Or in other words, F is m plus mg mu1 plus mu2. I think that's it. Yeah. So yeah, that's the pause. Okay, moving on. Sorry, a bit rushing here, but hopefully that makes sense. A block of 4 kilograms lies on a rough inclined plane, 25 degrees to the horizontal. A force is applied parallel to the plane upwards. So there's a force, 60 newtons, pulling that way. The coefficient of friction is mu, is 0.35. 4 kilograms is the gravitational force, mg, going downwards. And there's a normal reaction force acting on the block. Normal reaction goes this way. And the friction force is going this way, which is mu n. And we can split this force into components. If this is theta, 25 degrees, so this is mg cos theta, and this is mg sine theta. So we can write down the forces along the slope. This is the x-axis, and this is the y-axis. In the x-axis, I'm gonna go a bit fast now, so please don't worry if you can't follow. Do watch my previous webinars if you are still confused. So it's accelerating in the x direction. So mass times acceleration is 60 minus mu n minus mg sine theta. So force is pulling up the slope minus force is pulling down the slope. In the y direction, you have the normal reaction force minus the mg cos theta, and that's equals to 0 because it's not accelerating in that direction. It's not for going up or down. So from here, n equals mg cos theta, and we can use that in the first equation. So ma equals 60 minus mu mg cos theta minus mg sine theta. And here we can calculate acceleration. Just as simple as that. Acceleration is this. So, and you know all the values. So it's 60 minus 0.35 times 4 times 10 times cos 25 minus 4 times 10 times sine 25 all over mass, which is 4. And you get a value. The force is removed. Find the acceleration of the block as it moves down the slope. So now the force is removed. So B, now there's the gravitational force, mg. There's a frictional force going up the slope now, mu n and n. And in this case, you break it down. And this is mg cos theta and mg sine theta. So there are only two forces acting in that direction. So mass acceleration is mg sine theta minus mu n. So acceleration is mg sine theta minus mu n, and n is equal to mg cos theta. So mu n, which is mg sine theta minus mu mg cos theta. Mu mg cos theta divided by m. And that's the answer. So obviously you just put in the numbers, you get something. Now, this is one of my favorite questions. A circular hoop. So it's like a hula hoop. I'll try to demonstrate with a ball. So if I throw the ball and give it a backspin, the ball will decelerate and then accelerate back. Something like that. All right, so if I give it a backspin, you can see that the ball sort of accelerates that way. Okay, so that's what happens to a hula hoop. So you throw a hula hoop along the ground. I'm sure some of you played with hula hoops. If you haven't, go find a hula hoop and play with it. So if you give it a backspin and you throw it along the floor to the right, it will spin, slow down, and then accelerate back. So, and it's really fascinating to watch. So what are the forces acting? Well, because it's slipping, there's friction. And the friction force is to the left because, well, it has to be. If you think about it, the friction force has to be to the left, force of friction. And then there's a normal reaction force, and obviously the normal reaction force is equal to mg. So N is equal to mg, and the force of friction, because it's sliding, it's moving, is equal to mu N, which is mu mg. And the acceleration is to the left, so it's accelerating to the left. So Newton's second law says that mass times acceleration, mass acceleration is equal to, it's accelerating to the left, and there's only one force to the left, which is equal to the friction force, which is mu mg. Mass cancels, and acceleration is mu g. That's the acceleration of the hula hoop. And then, well, that's all you need to know, because now it's just a kinematics question. So if the friction force is, if coefficient of friction is mu, acceleration is that, and this initial, so time to stop is v0 divided by mu g, and then once it goes back, at some point it starts rolling. So it accelerates for some time and then moves at constant speed, right? So on the way back, the way back, it accelerates for some time, and then it returns and then starts rolling without. In this case, so the hula hoop launches at speed v0. So it launches at v0. It stops, then accelerates backwards, and then when it reaches speed v0 over 4, it starts rolling, so it doesn't accelerate anymore. So hopefully that makes sense. So if you draw a velocity time graph, it goes v0, it goes like this. Then when it reaches minus v0 over 4, v0, when it reaches minus v, it just rolls with no friction. Because the hula hoop is spinning backwards. So if I give the ball a back spin, the friction is that way because it's slowing the ball down, right? Like if the ball rolls normally, the friction is still that way. So if I give it a backspin, this movement between the ball and the floor means that the ball is attempting to kind of swipe the ground. The ball is like swiping that way, so its ball is propelling itself forwards. The ball is spinning that way, like just a wheel of a car. If a car wheel rolls forward, the friction from the road pushes the car forwards. Oh, that's another very important thing. When a car goes forward, the friction pushes the car forward because what else pushes the car? It's the friction force. It's the friction from the road. It's the grip from the road. And unfortunately, I ran out of time for the last one, but hopefully, it's an extra question anyway. It's one of the optional questions at the end of the paper. So I'll leave it to you. Oh, thank you for your attention. Hope that was useful. I hope I didn't lose you on the way. And so I'll see you, I think, in 2 weeks' time. Let me double check. So Newton's laws, the next session is on the 16th of February. It's solving equations. So I think that's 3 weeks' time. But I'll see you. All the best. Thank you.